Hi, everybody. Let's learn a little bit about 7.2, sampling distributions of sample proportions. And just like in 7.1, we are going to have to use our statistical imagination a little bit to understand these concepts. All right, so the sampling distribution of the sample proportion p hat describes the distribution of values taken by the sample proportion p hat in all possible samples of the same size from the same population. Now, if you know your combinatorics, if there's a large population and a fairly large sample, there are a lot of different combinations, thousands and thousands, and sometimes millions or billions or trillions of possible sample proportions. But luckily, after about 100, 500, 1,000 or so sample proportions, we get a really good idea what the sampling distribution of p hat looks like. So let's look at this example. Here is the approximate sampling distribution of the sample proportion of pennies from the 2000s in 50 samples of size n equals 20 from a population of pennies, right? So if you can imagine a big, huge, like bucket of pennies, and you randomly selected 20 of those pennies and found the proportion that were from the 2000s and marked that sample proportion. Say it was this one right here. And then you did that again, and you got this proportion, and then you did it again, and you got this sample proportion, and you did it again, you got this sample proportion. And if you did that 50 times, this is what the sampling distribution would look like. And that, again, that's not the complete sampling distribution, that's just for 50 samples. All right, so some properties that are really important that are really going to help us out with making calculations. If we choose an SRS, remember that stands for a simple random sample of size n from a population of size capital N with a proportion p of successes. Let's let p hat be the sample proportion of successes. Then the mean of the sampling distribution of p hat is equal to p. It's equal to the population proportion. Or the standard deviation of the sampling distribution of p hat is equal to the square root of p, remember that's the population proportion, times 1 minus p, again, p is the population proportion, divided by n, which is the sample size. As long as the 10% condition is satisfied. Remember we learned about that. That n is less than 10% of the population size. And if we want to interpret in context, we're going to say something like the value of sigma p hat measures the typical distance between the sample proportion p hat and the sample proportion p. The sampling distribution of p hat is approximately normal as long as the large counts condition is satisfied. Remember, that's n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. All right, so we know the mean, we know the standard deviation, we know the shape, and for those last two, we just have to have a couple conditions met. We need the 10% condition and we need the large counts condition. The two conditions mentioned in the previous slide are very important. Let p hat be the sample proportion of successes. The large counts condition is if we assume that the sampling distribution of p hat is approximately normal, when it isn't, any calculation we make using a normal distribution will be flawed. And the 10% condition, when we sample with replacement, the standard deviation of the sampling distribution of p hat is exactly equal to this formula right here. But when we sample without replacement, the observations are not independent, and the actual standard deviation of the sampling distribution of p hat is smaller than the value given by the formula. If the sample size is less than 10% of the population size, however, the value given by the formula is nearly correct. All right, so that's why we need the 10% condition and we need the large counts condition. Let's get to an example. All right, let's describe the sampling distribution of p hat. According to the National Center for Education Statistics, 20% of students who recently earned bachelor's degrees were business majors. Imagine taking an SRS of 300 students who recently earned bachelor's degrees and calculating p hat, which is the proportion of students in the sample who majored in business. So for part A, we want to identify the mean of the sampling distribution of p hat. That should be no problem. B, calculate and interpret the standard deviation of the sampling distribution of p hat. And we're going to verify that the 10% condition is met. We always got to do that if we want to use the formula. And C, we're going to describe the shape of the sampling distribution of p hat and justify our answer. So before we do that, and if you're following along on this slide, you could click here and check out this Desmos, which is right here. Let me click some of this stuff off. And I wish I had this already set up for you guys, but I didn't. And so, right, I'm going to select a sample of 300 people. The probability that they were business majors is 20%, right? So right here, I have one sample proportion, right? And that's about 0.21 or so, right? And I'm going to take a different sample of size 300 and, oh, I can't slide very accurately. So now I have 4 samples total. Each sample, each one of these dots is a sample proportion that comes from a sample of size 300. All right, so I can see that because of sampling variability, they're not all the same. This one is 0.17, so 17% of these 300 were business majors. This one's about 0.21. We saw that one already. This one's about 0.2167, just slightly larger. And this one's about 0.2433. All right, so what I'm going to do here is I'm going to collect 1,000 samples. And each one of those samples will be from a sample of size 300. And I'll calculate the sample proportion of business majors in that sample. All right, so let's do that. We can do it really quickly and watch it on the graph. It looks great. I'm going to zoom in a little bit. All right, so that dot plot is 1,000 samples. Each sample is size 300. And I could see the sampling distribution, or start to see what the sampling distribution of sample proportions looks like. So I can see I'm getting that like bell shape that I would expect by what we just learned about in the last slides. So let's look at this in terms of a histogram. All right, so this histogram looks even more nice and more bell-shaped. And if I take a normal distribution and I have a mean of p, remember p is the population proportion, which in this case is 0.2, and I have a standard deviation of the square root of p times 1 minus p over n. Remember, that's the standard deviation formula that we learned in the previous slide. And I superimpose that over, I can see that that does a great job of estimating the shape of this histogram, right? And you guys know by large counts, if I selected more and more and more samples, each of size 300, this normal curve, would do a better and better and better job of estimating the shape of this histogram, the resulting histogram, right? So I can see from this, this has a center right at 0.2. The mean of the sampling distribution, the mean of all these sample proportions is going to be 0.2. And I can use this formula to find the standard deviation of all these sample proportions, right? So let's go on and answer some of these questions. In the slide, I just have some screenshots of that Desmos. And our solution would be for part A, the mean of the sample proportion. So mu of p hat is equal to 0.2. No problem. It's always just equal to p. B, we're going to find the standard deviation of the sampling distribution. Assuming that n is equal to 300 students is less than 10% of all students who recently earned bachelor's degrees. Remember, we're going to verify that the 10% condition is true. We're going to use the standard deviation formula right here, and we're going to get about 0.0231. And so in SRSs of size 300, the sample proportion of students who recently earned bachelor's degrees and majored in business will typically vary by about 0.0231 from the true proportion of p equals 0.2. And then lastly, because 300 times 0.2 is equal to 60, which is greater than 10, and 300 times 1 minus 0.2 is 240, which is also greater than or equal to 10, the sampling distribution of p hat is approximately normal. So here we had to verify the large counts condition. And because that condition is true, we know the sampling distribution of p hat is approximately normal. All right. So let's go on to another example where we're going to actually apply some of what we just learned and then make a normal calculation. In 2016, more than 200,000 students took the AP Statistics exam. Of these students, 14% earned the highest score of 5. Find the probability that a random sample of 300 students who took the 2016 AP Statistics exam would indicate that 15% or higher earned a 5. Right? So we know the actual proportion who scored 5, and we're going to take a sample of 300. What's the probability that our sample proportion indicates is 15% or higher? All right, so in this case, again, we know that mu of p hat is equal to 0.14. That's the population proportion of 0.14 that we just learned, that we were just told. We know that 300 is less than 10% of all AP statistics exams takers, less than 200,000 or so. And so we can calculate the standard deviation of that distribution. Applying the formula, we're going to get about 0.02. And because n times p is equal to 300 times 0.14, that's 42. That's greater than 10. And then also n times 1 minus p is 258, which is greater than 10. The distribution of p hat is approximately normal, right? So we applied the large counts condition. We want to find the probability now that p hat is greater than 0.15. That's just a straightforward normal calculation. So we're going to have a normal CDF. Our lower bound is going to be 0.15. Our upper is going to be infinity, or 11111. And the mean of this distribution is 0.14, right? That 0.14 comes from right here. And the standard deviation is 0.02. That 0.02 comes from right here. We plug that into our calculator, and we get about 0.3085. Right? We definitely want to make sure we draw a normal sketch and shade it anytime we are asked to make a normal calc. So I will be expecting that on all of your exams and free responses. So get in the habit of doing that on your homework. This one's going to look like this. See, we have the center at 0.14. That represents the mean, and 0.15 would be about right here. And we're looking for the probability that p hat is greater than 0.15. That's the shaded area. So if we answer in context, we'd say there is about a 30.9% probability that a sample proportion from a sample of size n equals 300 will be greater than 0.15. All right. Now we're going to move on to a slightly more complicated idea, and we're going to take the sampling distribution of a difference between two sample proportions. So in this case, we have two different populations that we're sampling, and we are going to combine those random variables, those sample p hats, right? Well, the distribution of p hat 1 minus p hat 2 is approximately normal if the large counts condition is met for both samples, right? So that's n times p is greater than 10, and n times 1 minus p is greater than 10 for both distributions. The mean of the sampling distribution is pretty simple to find. It's just equal to P1 minus P2, the population proportion of the first population minus the population proportion for the second population. And the standard deviation is given by this beast right here. And that's the square root of this plus this. It's always plus. It's never minus. Always plus. And so this is also true if the 10% condition is true for both populations and both samples, right? We need sample size 1 to be less than 10% of population size 1, and sample size 2 to be less than 10% of population size 2. A lot of words there. All right, so note that the formula for the standard deviation is exactly correct only when we have two types of independence. Independent samples, so we can add the variances of p hat 1 plus p hat 2, and independent observations within each sample. When sampling distribution without replacement, the actual value of the standard deviation is smaller than the formula suggested. However, if the 10% condition is met for both samples, the difference is very, very small, and we're just not going to worry about it. All right, so it's very important to check the 10% condition. All right, so here's our last example. Describe the sampling distribution of the difference in two sample proportions. In a very large high school, the junior class has 800 students, 54% of whom are female. The senior class has 300 students, 49% of whom are female. The student council selects a random sample of 40 juniors and a separate random sample of 35 seniors. Let p hat junior minus p hat senior be the difference in sample proportions of all females. We want to find the shape of the sampling distribution of p hat junior minus p hat senior. Why does it have that shape? We know find the mean of the sampling distribution of the difference in sample proportions. And we want to estimate the probability that the proportion of all females in the sample from the junior class is less than the proportion of females in the sample from the senior class. All right, if you're following along and you click on this Desmos, it will take you to this right here. So this histogram represents the sampling distribution of females in the junior class. Okay, this is the sampling distribution of sample proportions of juniors in the of females in the junior class. I'm going to click here, and this is the sampling distribution of the sample proportion of females in the senior class. So there is some overlap. And so if you imagine taking a simple random sample and you get a result from this red distribution, and a different simple random sample, and you get a result that is in this blue distribution, and you subtract the difference, you would get this green distribution right here, right? And so this is the distribution that I'm going to make my calculations off. So I'm going to clear this out so we can focus a little bit more. All right, so I have this distribution right here. I can see it's got that beautiful, beautiful bell shape. If I make a nice normal curve over that, I see it does an excellent job of estimating that. And remember, this is just for 1,000 samples. If I took more and more and more samples by the law of large numbers, my curve would do a better and better job of estimating my sample proportions, this distribution. All right, so what I want to do is find the probability that I have less, that I have that this is less than 0, all right? And if I click on that, I can see that this shaded area right here represents that the seniors are less than the juniors. That's going to come out to be 0.3325. All right, so let's look at how we would do that on our paper. All right, so for part A, we want to describe the shape. It's approximately normal because of the large counts condition, right? We have n times p, and n times 1 minus p is true for both distributions, for both samples. I have 21, 18.4, 17.15, and 17.85. All of those are greater than 10. So I want to show that to be able to say that, yes, this is approximately normal. It's mandatory that you state that in order to make a normal calc. And then because 40 is less than 10% of all juniors and 35 is less than 10% of all seniors, we can apply this standard deviation formula. From that, we're going to get about 0.1155. So if we interpret that, the difference junior minus senior and the sample proportion of females typically varies by about 0.1155 from the true difference in proportions, which is 0.05. Right, that 0.05 comes from right here. All right, so we have a mean of 0.05, we have a standard deviation of 0.1155, and we know that that shape is approximately normal. So let's go on and make our calculation. We want to find the probability that p hat junior is less than p hat senior. And we know if we just do a little bit of subtraction, if I subtract this p hat over to this side, I end up with this, which was that distribution that I just showed you on the Desmos. Here's another version of that distribution. So basically, when we want to find this probability, I can use a normal calculation to do that, normal CDF. My lower is going to be negative infinity, or negative 1,111,111. My upper bound is going to be 0, which is going to be right about right here. That's my boundary. My mean is 0.05, my standard deviation is 0.1155. And from that, I get 0.3325. I want to interpret that in context. We're going to say there is about a 33.3%, if I round this a little bit and write it as a percent, 33.3% probability that a sample of 40 juniors has a proportion of female students that is less than the proportion of female students from a sample of size 35 from the senior class. All right. A lot of stuff today. I hope that was helpful. And thanks for watching.